All right, well, we're going to pick up right where we left off there. Last time, we talked about a variety of algorithms, right? We talked about scaling, and then we talked about shortest augmenting paths. And these were both algorithms that achieved polynomial time bounds for finding maximum flow, but different kinds of polynomiality. Right? So scaling gave us a weakly polynomial algorithm. Okay. Its polynomial time, when you write in the size of the input, when you write down your numbers in the standard binary representation. On the other hand, the shortest augmenting paths algorithm is strongly polynomial, right? It can be executed even over real numbers if you have a model of computation where you're able to store real numbers, right? So this shortest augmenting path algorithm does a bunch of additions and subtractions of real numbers. Those are the only operations that it actually performs. I guess probably some, yeah, I think that's it. And its running time is a polynomial that does not depend at all on the values of those numbers. It depends only on the size of the input graph, right? So the scaling algorithm had a running time that looked something like mn times the log of the log of the capacities in the graph. The shortest augmenting paths algorithm had a runtime that was something like m squared times n, right? A single augmenting path took linear time, and you had to perform about mn of those shortest augmenting path steps, right? And so both of these are polynomial time bounds. They therefore improve on the pseudo-polynomial bounds that we started with, right? Which are only polynomial if you write the numbers down in unary notation. The runtime is proportional to the values of the numbers, as opposed to being proportional to the log of the values of the numbers. Okay, so this is the landscape. Now you can see here that, you know, aside from the log u term, the scaling algorithm, and before that the max capacity augmenting path algorithm, right? They both have runtimes that look kind of like, sorry, this is m squared, right? Not mn. Yeah, m squared. They have runtimes that look like sort of m squared, whereas the shortest augmenting path algorithm costs us another factor of n, right? And so the shortest augmenting path algorithm is strongly polynomial, but it's a worse polynomial than you're able to achieve with scaling, right? So it might be nice to have the best of both worlds, to be able to get a good polynomial that is also a strong polynomial, or just in general to get better time bounds. And so the last thing that we talked about on Wednesday was a way to improve on these shortest augmenting path algorithms by getting more benefit from the shortest augmenting path calculations that we were performing. I introduced you, might as well use a new board. Right, so I introduced you to this idea of blocking flows. And the idea of blocking flows is if you're going to do all of this work to compute shortest augmenting paths, let's find a way to get more benefit from that computation than just by saturating one augmenting path, right? We're getting a lot more information, right? And so what we do is, given the current graph, which after we do some flow computations, we will have some kind of residual graph. We compute, we use a BFS, breadth first search, to compute layers of this admissible graph. Right, so we start at S, and we see everything that can be reached from S. That's layer 1. Then we look for everything that can be reached from those vertices. That gives us a layer 2. And so forth. We just keep on going through the layers of our breadth first search. And eventually we will find our way to the sink. There may be some other paths that go off in other directions, but we don't care about them because we're interested in finding flow to the sink. So paths that can't reach the sink, it doesn't matter. Okay. There may also be paths that eventually reach the sink through a much longer path than the shortest path, but we're not interested in those either because we're still pursuing this idea of shortest augmenting paths being good ones, right? So we don't worry about these longer paths either, okay? So I've drawn these arcs in the admissible graph that go forward from one layer to another layer. And these are called the admissible arcs. Now, there are other arcs in this graph. Where can they go? Yeah?
You go back a layer or between two nodes in the same layer?
Good. So I might have some arcs that go backwards, right? Any possible distance. I might also have arcs that stay in the same layer. Yes? An arc is an edge. Sorry. Arc is the term that's often used when you're talking specifically about directed edges. Okay? And for this lecture, I definitely want to stay focused on directed edges. Okay, so we have backward edges, we have sort of vertical edges. Can we have edges that skip over several layers and go forwards? No. How come? Right. If we did have such an edge, we would have a shorter path than the ones that we found, right? Or to put it another way, since we're doing breadth first search, right, any edge that does go forward can only go forward one layer because it defines the next layer. Yes? All right. So we have this admissible graph with its admissible arcs. And we find this as we're doing a shortest augmenting path computation, right? We're going to build this structure kind of as a side effect. And once we found it, right, what are the shortest paths in this graph?
Everything of like those like dark edges.
Exactly. So shortest paths are admissible arc paths. Any shortest path is made of admissible arcs only. Any path that is made up only of admissible arcs is the shortest path because each edge of that shortest path traverses exactly one layer, right? So already this seems promising because our shortest augmenting path algorithm keeps on finding shortest augmenting paths over and over again. But if we have this admissible graph, like if we find a shortest augmenting path and saturate it, well, we still have the rest of the admissible graph. And so we could look for another admissible path, and that would also be a shortest path, right? And we would keep on finding more admissible paths in this graph. As long as we can, we keep on finding shortest paths, right? Remember, we already proved that if you augment on a shortest augmenting path, the distance doesn't get smaller between S and T. So all of these paths are going to stay shortest augmenting paths as we find them, right? So we can, in fact, find a maximal set of these admissible paths. And this is called a blocking flow. Sorry, we find and saturate. And this is called a blocking flow. It is a flow that saturates a maximal set of paths in this admissible graph. Okay? And another way to think about that is that it saturates at least one edge. On every admissible path. Right? If there's an admissible path where you didn't saturate an edge, then you could use it to send more flow. So your blocking flow would not be maximal in that case. Right? Okay, so I said we're finding a maximal flow in this admissible graph. How does that differ from a maximum flow in this admissible graph? Yes?
So maximal would mean that we can't improve this flow anymore by adding more, but it does not mean that it's the maximum, as in if we chose some paths differently, we could be able to improve.
Correct. And with when we talk about maximum flow, right, this improvement happens because we don't only add flow to edges, we sometimes take flow off of edges because we send flow through the residual graph, right? So finding a maximal set of admissible paths, a maximal flow, is going to be easier than finding a maximum flow because we don't have to consider this possibility that maybe we can make things better by removing flow from some of the edges that we're already using. Okay? So that's what a blocking flow is. What is its benefit? Well, suppose that we have found a blocking flow, okay, and we send all of that flow. What changes in the residual graph as a result of that blocking flow? So the key claim is that a blocking flow increases the ST distance in the new residual graph. Whatever the distance was before you computed the blocking flow, if you now compute a blocking flow, the new residual graph has a larger ST distance than it did when you started. Okay? So if you think back, with shortest augmenting paths, all we could prove about a particular shortest augmenting path was that the distance did not decrease. But if you just find one augmenting path, one shortest augmenting path, the distance might not increase. But if you find a blocking flow, the distance actually increases. Okay. Now, if the distance increases every time you find a blocking flow, what does that tell us if we want to find a maximum flow? Yes?
You only have to do this, you only have to find n blocking flows?
Exactly. N blocking flows find a max flow. Okay? And this is to contrast with Mn shortest augmenting paths. Right? Okay, so why the claim? Why does finding a blocking flow increase the distance from S to T? Well, we already know that it doesn't decrease it because it's a series of shortest augmenting paths. But why does it increase it? Well, what changes when we add this blocking flow? Right? So the blocking flow removes, by saturating, some admissible arcs. Right? Hi there. But that's not the only change that it makes to the graph, and so we have to worry. Like, removing arcs is certainly not going to decrease the distance, right? We don't know that it's going to increase it, but removing arcs is not going to decrease the distance. But what other changes happen in this residual graph as we add in the blocking flow? Well, this is what makes max flow so complicated, right? Is that we can create new edges, right? When we send flow through an edge, we create a residual edge. What kinds of edges does our blocking flow add? What can we say about those edges? What was that?
It goes back along the...
Right. It adds backward edges. And what I mean by that is they go backward a level edges, right? Because the only edges that we add flow to are edges that go forward a level, which means that the only residual edges that we create are the reverse of those edges, and so they go backward a level. Okay? So we take this admissible graph, we remove some of the forward edges, and we create some backward edges. Right? What does that do to the distances? Can it decrease the distance? Yeah?
No, because if this backward edge, if we actually use it in a path, well, it takes us backwards. So if we have to do an additional step then to counteract, so it would actually be too longer.
Good. Well, could we do so? That's exactly right. So using a backward edge takes you a step backwards, and so you're kind of behind, right? The admissible paths here are very efficient. Each step takes you forward one level, right? And that gives you shortest path. Now we're adding in a backward edge, right? So we're wasting a step and actually losing a level instead of gaining one. So we're now 2 behind where we should be. Can we make that up by using some of the other edges in the graph? No. How come?
If you use other edges in the graph to reach T, you would have used it in shortest path before.
Well, if I'm somewhere in the graph, there might still be a path to T, right? The blocking flow guarantees that there's no path from S to T. But if I've made it part way, or sorry, let me be careful. The blocking flow says there's no admissible path from S to T. However, we might have created some new paths from S to T that use backward edges. Why is it longer? That's what I'm trying to get at. Yes?
So like if you keep track of the levels, each admissible one can only add 1, while each one like minuses. So
Exactly. The admissible arcs only advance by 1 level, right? You can't, there's no edge that takes you more than 1 level, right? And this is still true in your new residual graph, right? Because the only edges we created were edges that go backward, right? We certainly don't create any double forward edges. Right? We don't add any residual capacity that moves forward by multiple steps, or even by 1 step. So still the best you can do in a single step is advance by 1 layer. And so if you ever lose a tempo by going backward a layer, or even by going vertically, you're never going to make it up and and achieve the distance of the previous shortest paths. right? So that tells us that we're not getting any shorter paths. And in fact, if you play with that argument a little bit, you can see why you're getting a longer path, right? So consider any path in the new residual graph. Okay. Now that path is made up of some of the arcs that were admissible before, but it has to be made up of some other arcs, right? It can use some admissible arcs, or sorry, what I can say is it must use at least one non-admissible arc. Why does it have to use a non-admissible arc? Exactly. So there is no path made up only of admissible arcs. Right? And so that means it loses a tempo in terms of going through the layers, right? What I should say is the previous and now, since there are no multi-forward edges, you can't make it up. And so whatever this path is, because it lost at least one tempo, in the worst case, in the best case, it's going to use a vertical edge. It's not going to go backwards, but it's still one behind. And that means that it is at least one longer than the previous shortest paths. So every path is at least one longer, which means that the distance is at least one more. Yes?
When you say you must use a non-admissible arc, by that you mean it was not admissible and now it's admissible?
Correct. So all of my discussion here has been in terms of this layered graph. And these are the admissible arcs that I'm talking about. Okay, this is a good and important point. Right? So the proof is with respect to this layered graph. And based on that proof, I can conclude that the distance from S to T has grown. So of course, what this means is I am now going to build a new layered graph, which is going to make a different set of admissible arcs. And I'm going to compute a blocking flow in that new layered graph. Make sense? All right, so this tells us why blocking flows are good. Now we can start thinking about how to find them. Okay. So it's often useful when you're working in combinatorial optimization to think first about the unit capacity case. Right? We've already seen a good strategy for going from unit capacities to everything else, and that tells you that if you can gain some insight from unit capacities, you can perhaps get to solutions to the whole problem. Even if scaling doesn't work, you gain a lot of insight from this. So what would be a natural general approach to looking for a blocking flow if I gave you a layered graph like this? DFS, right? So I start at S, and I start walking forward, right? And one of two things might happen, right? One possibility is that I'll get to T, and I'll say, I found a path, right? What do I do if I found a path? Well, I can't remove the whole path. But I can block that path, right? If I saturate that path, if I find the minimum capacity on that path, or sorry, this is for the unit capacity case. So I guess, yes, I can remove all of the, right? I'm going to send 1 unit of flow, and that means that I will saturate all of the edges on that path, and they will be gone now, right? Now what do I do? Now I start again back at S, and I look for another path. Okay, so I start my DFS again. And, well, I might get to T again. We already covered that case. What else might happen? Well, I might hit a dead end. Right? I might get to a vertex that has no outgoing edges. Right? What do I do in that case? Well, I'm doing a DFS. What do you do when you hit a dead end in DFS? I backtrack, right? So, I went out here. I hit this vertex. It has no outgoing edges, so I'm dead. I'll backtrack. Okay. Did that backtrack tell me anything besides the fact that this vertex is useless? The edge is also useless, right? If I took an edge to a dead end, then that edge cannot carry any blocking flow. So I can delete this edge, right? That'll just prevent my having to pay attention to it in the future. Okay? So now we've got the pieces of our blocking flow algorithm. Okay? Our steps are to advance on an unexplored edge. Okay. Actually, let me say, yeah, let's just call it steps for now. So we advance on an unexplored edge, and if we reach T, then we found a path. And so we can augment on it. And we can delete the path edges. Right. Yes, question?
We start at T in the beginning, go backwards.
It's symmetric. You can do all of this starting from T and going backwards. It's the same as reversing the edges, right? A blocking flow from S to T, if you reverse all the edges, you're looking for a blocking flow from T to S. Unfortunately, there is, because there could be edges out here. I mean, they wouldn't be in your layered graph. If you build a layered graph from S, then you won't find them from T. But remember, we're now proceeding to delete edges. And so we might create situations like this, even though they didn't exist at the beginning. Okay? Okay, so if we reach T, we augment and we delete the path edges. If we hit a dead end, then we can retreat. And we can burn our bridges behind us. We can delete the retreating edge. Okay, so the steps are to advance, to augment, and to retreat. And you put those together and you get a blocking flow algorithm. Yes?
So to delete the path edges, it is only for the unit capacity case, right?
Correct. We are starting with the unit capacity case, and then we will use the insights that we get from it in order to solve the general capacity case. Okay. And of course, after you retreat, you're on a new vertex, and you resume the attempt to advance from where you currently are. Okay. And if you can't advance from where you currently are, then again, you retreat. And you just keep on retreating until you can switch back to advancing. So the question is, how much time does all of this advancing and retreating take? Sorry, is that a question or an answer? O of m. Let's think about why. Let's break it into parts. So what can we say about the augment time? How much time do we spend, once we have found a path, how much time do we spend updating the flow on those edges and deleting those edges? It's order m, because there is at most one augment per edge. Right? What about the retreat time? That's also m, because each time we retreat on an edge, we delete it. Right? And finally, what about the advance time? Why?
We never advance on edge twice.
Can you tell me why we never advance on an edge twice?
Well, if we advance it on an edge and at some point retreat, then we will not advance it over it again because we deleted it. And if we advance on an edge and we reach T, then we will also delete it.
Exactly. So the way I like to say this is that we can always charge the advance to the retreat or augment that follows. Right? Once you advance on an edge, either you will retreat on that edge, or the only reason you wouldn't retreat is if you got to T and then you would augment through that edge. Yes?
That I'm actually O of m because the T is the small m.
Sorry, the retreat time? So this is over the full execution of the blocking flow algorithm. So, again, you start at S, you advance. If you ever get to T, you augment, and now you go back to advancing from S, right? So you're absolutely right that a single augment only takes n time at best, at worst, because there are at most n layers, right? So one augment is only order n, because there are n layers. And that's actually worth remembering for later, but it's not important now. Right now, we're just talking about the overall time of the entire blocking flow. Okay? Yes, a question.
So after you do the DFS and you find a shortest path from S to T, you start over the DFS, right?
Correct.
Okay.
You have to, right? Because those edges that you used are now gone because you augmented through them, so you have nothing. Okay. So this is very nice, right? So now we can put some pieces together, right? So one blocking flow takes order m. We need n blocking flows for a max flow. And that means it takes us overall order mn time to compute a max flow in unit capacity graphs. Any questions? Yes?
So if I understand correctly, admissible edges are those that are contained in at least one shortest path.
They don't have to be because they might reach dead ends. Right? I mean, it depends. You don't need them, right? If you reach a dead end, then the edge is not useful, so you could throw it away. But technically, I'm doing this breadth-first search, right? And wherever the edges end up, I have these layers, whether or not I get to T. Right? It's not worth my actually keeping track of what can reach T and what can't. I'll discover that during the blocking flow. So in fact, the admissible graph is going to look more like this when I first compute it. I'm going to have I can stop when I get to a layer of T because nothing beyond it is possibly admissible. But I may have other vertices at the same level of T and paths that go to those vertices but don't reach T. Yes? Well, again, I don't need to delete them initially. My blocking flow is going to end up deleting them because they dead end without reaching T. Yep.
The unit case. So it is still like slightly better, only slightly better than scaling.
Good. So, well, even before scaling, did we achieve anything, right? If you think about unit capacity max flows, then it seems the plain augmenting paths algorithm seems like it achieves order mn, right? I mean, in a graph, at least in a graph without parallel edges, right? In a simple graph, right? The maximum degree is n, which means that the maximum flow is n, which means that standard augmenting paths finish in order mn time in the unit capacity case. So what good is blocking flows doesn't seem to have improved. Well, blocking flows does not require this simple graph criterion. So blocking flows, the order mn time bound applies even in graphs with parallel edges, right, where the value of the flow could be much larger than n. Okay, so it's not as dependent on the value of the flow. What we've done so far is still dependent on unit capacities. But there are other reasons that this blocking flow approach is better. One is that it will just work better in practice, right? This blocking flow algorithm is going to find a whole bunch of flow after one shortest path computation, after one BFS or one DFS, whereas the standard augmenting path algorithm will just find one path at a time and then run another DFS. So it's going to take a lot, it's going to be a lot slower in practice. But we don't get a better theoretical time bound unless we change the analysis. So another way that blocking flows are better is that we can actually prove other bounds than the order mn bound. So here's another bound for you. Okay. And this bound actually generalizes one of the key insights of shortest augmenting path and blocking flows, right? So what those algorithms rely on is the idea that if you can get the distance from S to T to exceed n, it means there's no flow, right? You have found a max flow because there can't be a path from S to T if the distance is larger than n, okay? But let's try to generalize that. Suppose that I tell you that the distance from S to T is very large, okay? So suppose that the distance from S to T is greater than or equal to k. Can I say anything at all about the residual max flow, or the amount of max flow in this residual graph? Unit case. Let people think about this one. Right, so what's the generalization of if the distance is n, there is no flow? Yes?
The residual flow is bounded by m over k.
Exactly, right? If the distance is at least k, well, why is that true? Why is the residual flow at most m over k? Okay, so that's one way to say it, right? If I've got this distance, if I've got this k distance in the layered graph, right? One of the cuts, right? The layers divide up the edges. So one of the layers can only have m over k edges in it. And that is a cut. And that means that the min cut is at most m over k, which means that the max flow is at most m over k. Now, there's another way to argue this without talking about cuts.
Every path must have at least
Exactly.
So we can have the most MOK paths, all with unit capacity, and so we have this balance.
That's right. So now, I mean, so you can use the cut argument, or you can use the flow decomposition argument. So everybody happy with that argument? That if the distance is large, there's not much flow? Well, so how do we use that? If there's only m over k units of flow left, how much time is it going to take to find that flow? Well, every blocking flow adds at least 1 unit of flow, right? There's always at least one shortest path. So each time I find a blocking flow, I'm adding a unit to the flow, or I'm reducing the residual flow by 1. Right? So how many of these can happen if there's only m over k units of flow left? Well, only m over k of these blocking flows. Right? So k blocking flows increase the distance to k. And after that, m over k more blocking flows decrease the residual flow to 0. And so we're done. So we need at most k plus m over k blocking flows to find a max flow. Now you notice that this argument works for any value of k. Right? So what would be a good value of k? Square root of m, right? 2 root m blocking flows find a max flow in order m to the 3/2 time. Any questions? Oh, I'm sorry. This is actually an O. So I put a squiggle on when I don't want to write log factors. But in this case, since we're talking about unit capacity graphs, there are no log factors. Okay. So this bound, well, is often better than the mn bound, right? In any kind of sparse graph, m is going to be less than n squared, and so m to the 3/2 is going to be better than mn. Okay. There is an alternate analysis. In simple graphs, those are the ones without parallel edges, you can use a similar argument to prove an mn to the 2/3 time bound. So this is strictly better than the mn time bound. And finally, there's a special case for max flow where this turns out to be really useful, which is what's called the bipartite matching problem. So in the bipartite matching problem, you're given a bipartite graph. Okay. Maybe you're trying to pair up roommates at MIT, and you've got a group of tall people and a group of short people, and you want to make sure that they're matched up so that they can discuss each other's perspectives on life. And so you've also got this sort of compatibility metric, which says, who has the same sleep schedule or something like that, right? Or who has opposite sleep schedules might be better. And you want to find a maximum matching of these pairs. That is, you want to match up as many pairs as possible. Which is just to say you want to find as many edges as possible, such that no vertex is involved in two separate edges. Okay. Now, it turns out that you can actually formulate this as, you can solve this by transforming it into a max flow problem. Does anybody see how to do that? Yes?
Add a source connected to all the left-hand side, and a sink connected to all the right-hand side.
Right? And now, if you compute a max flow from S to T, okay, now we actually have to be a little bit careful here. We thought we had a really fantastic result a while back, but it was because we weren't being careful about this. You also have to direct these edges. So if you leave them undirected, then strange things can happen. But if all the direct edges go from left to right, okay, then if you think about it, there's at most one edge going into every left vertex. So you will use at most one edge coming out of every left vertex. For the same reason, your flow will use at most one edge coming into every right vertex, which means that the set of edges that are used in the middle will form a matching. And the value of the flow will just be equal to the number of edges that you use. So a maximum flow will correspond to a maximum bipartite matching in this graph. Okay. And for graphs that are constructed like this, they're called unit graphs. Because every vertex has either in degree 1 or out degree 1. And a similar analysis to the one that we did shows that the blocking flow algorithm will compute a max flow in order m root n time in such graphs. So again, strictly better than the standard augmenting paths algorithm. Yes?
Just a quick question to recap. What do the edges between the nodes on the left and the right mean? Is that just like compatible possible?
Yes, those are the edges you are allowed to use to make a match. Yes?
So in this bipartite graph, the shortest path is always like 3 or something.
Well, no, because remember, as we add flow, we create residual arcs, right? And what do those residual arcs look like? They're actually going to go backwards. And so you might have a path that goes forward and backward and forward and backward and forward. So the shortest paths are actually going to get longer as you compute blocking flows. That's exactly what blocking flows do. Okay? Yes?
How you get the square root of n, like.
So it requires an analysis similar to the one that we just performed. Okay, that sort of it sort of talks about these sort of layers and argues that there has to be a small layer somewhere. Okay, I may put that on your homework next week. I'm not sure. I have to decide about that one. Okay. All right. So that's kind of the end of the story for blocking flows on unit capacity graphs. They're already giving us something better than standard augmenting paths because of the way they take more advantage of each shortest path computation to find a lot of flow instead of just finding one augmenting path. Okay? The obvious next question on the table is, what about graphs with capacities? What can we do for that case? And so we will explore that after we take a short break. Each time you find a blocking flow, it increases the distance from S to T.
But like, I'm a bit confused. If we already have the distance at least.
No. So K blocking flows increase the distance to K, and then we're in this situation, so there's only M over K flows that we still need.
Oh, okay, so we don't a priori know this. Okay, we just
Mm-hmm.
Okay, that makes sense. I thought, yeah, I didn't realize that you were saying this was
Yeah, but it's clear now?
it's kind of like backwards and then
Sure.
forwards and then backwards again.
Okay,
I got a little bit confused by that.
sure, sure. Did you have a question?
What is this last comment on simple graph?
If you are analyzing simple graphs, you can prove a bound of order mn to the 2/3 for finding max flow.
Wait, so we are working on directed graph, right?
Yes, but you still, a simple graph is a directed simple graph is just a directed graph with no parallel edges.
Oh, right, we could have parallel edges. Okay, thank you.
Sure. I do not play chess at any level of at any professional level, but it is a term that I'm familiar with from chess. Okay, so just a quick reminder that if you have questions, please ask them while I'm lecturing because you will be helping your classmates, right? If you ask when I'm down here, then if you ask during break, then it only helps you. So just to make sure everybody's clear on this, the argument that I've made here is that if you run k blocking flows, that will force the distance to go up to k. And at that point, there is only m over k flow remaining. And so after k blocking flows, another m over k blocking flows will finish the algorithm. And that's true for any value of k, so we used root n because that gave us a good bound overall. Okay. Now, before I return to the lecture, just a logistical issue. You're, at this point, starting PSET 4, which means you're probably running out of collaborator capacity. Like, you know, we put limits on how often you could collaborate with somebody. So we're expecting a bunch of collaborator shuffling to happen now. And we are going to use the PSET Partners website to support that. If you go to PSET Partners, you can open up a group, and then people can join themselves into that group. Or conversely, you can look and see if there are open groups and just join into one. Okay? And then next Wednesday, when the next PSET goes out, if there are people on the site who have not yet joined a group, we will randomize anybody who's still there and looking for partners in order to create groups from the people who remain. In order to facilitate all of this, once you do find a group in the PSET Partner website, make sure you sort of inactivate yourself so that it's clear that you're not looking for a group, so that when we see who's left next Wednesday and we randomize, we're not putting people in who are already in a group. Does that all make sense? Any questions about it? No? Okay. I mean, it's funny. You saw in the email, I put out a question of some people looking for collaborators, and I got several responses. So I'll remind you that the PSET Partners website is there precisely for that purpose. If you're interested in finding a collaborator, go look. If you have collaborators, make sure you're inactive so that other people don't try to collaborate with you. Okay, so now we're done with the story of blocking flows for unit capacity graphs. Let's talk about general capacities. So if we have a solution for unit capacities and we've decided to tackle general capacities, what's the obvious turn the crank way to get a solution for general? Yeah? Yeah, we can try scaling. Actually, I should be a little more, right, this is not real, we're not going to talk about real capacities right now, but at least if you have integer capacities, then you can use scaling. You can use this idea that all of the numbers are represented in bits, and you can initially round all the numbers down to 0, which makes it really easy to find the max flow, right? And then you can unround by 1 bit at a time. And each time you unround, it's going to create some residual capacity. And now you can use a max flow algorithm in order to saturate that residual capacity and get yourself back to a max flow, right? But as we saw last time, right, when we did the scaling algorithm for max flow, since you're only rounding in 1 bit at a time, the residual capacity that you create is small, and so it's kind of like you're still working with unit capacity graphs. Right? So does this work as a general insight? Yes?
Depends on the size of the capacity.
Correct. So what we are going to be developing this way is a weakly polynomial algorithm, and I'll have some things to say about strongly polynomial algorithms next, but we're going to start with scaling to get a weakly polynomial algorithm. Okay. So actually, in order to talk about this scaling, let me take a closer look at the unit capacity case. So I said before that the blocking flow runtime is order mn, okay? But we can actually be a little bit more precise than that, okay? Notice that each augment finds, sends a unit of flow from the source to the sink. So if every augment sends 1 unit of flow, that implies that we have at most f augments if the flow value is f. And that implies that we only do order nf augment work. Correct? That's the point that I think you brought up, or somebody brought up, when I was talking about blocking flows, right? A single augment only touches n edges because the longest path in the admissible graph is n, right? So although if we look at all of the augments together might touch all of the edges, and so you can say all of the augments together take m. But if you look at just one of the augments, that's only going to take n. And that's going to be a useful piece of our argument for the scaling algorithm. Okay? So the augments cost order nf. The blocks, right? The retreats are m per blocking flow, so mn overall. So really, the runtime of the blocking flow algorithm is order n times f plus n times m. Okay. And so this wasn't important when we were talking about unit capacity graphs because the value of the flow was always at most m. But more generally, this time bound really shows you what's going on with blocking flows and why they're better than shortest augmenting paths, right? So there still is this nm term caused by the retreats, but we're only paying n per unit of flow that we find, as compared to the augmenting path algorithm, which spends m for each unit of flow that we find, right? So order mf for augmenting paths. Does that make sense? All right, so this is something that we can use in analyzing our scaling algorithm. Oh, sorry, I already have this one. Let's go over my report. So let's think about our scaling algorithm. We round to 0, and then we unround 1 bit at a time. And then when we unround a bit, we find a max flow in the unrounded residual graph. Right? Now, if you think back to the previous lecture, what can we say about the max flow that we're finding in a single step? That is, when we do our unrounding and we scale in 1 additional bit, what can we say about the max flow that we need to find? This is a replay of the argument for why scaling worked well with augmenting paths. So why did scaling work well for augmenting paths? Now is when we see who watched Wednesday's lecture. It's OK, I'll wait an hour. You can watch it now. So what was the key insight, right? So the scaling algorithm, in general, we know it has a small number of phases, right? The number of phases of the scaling algorithm is just the log of the maximum capacity, right? But we also needed to argue that each phase was fast. So y, when we looked at the augmenting paths algorithm, was a single phase, that is the max flow computation after you unscaled a bit, right? Why was that single phase fast? Yes?
How much flow is added when you add 1?
And so can we reconstruct that argument for why scaling in a bit in each number, in each capacity, does not add a lot of flow? Right, so before we scale in a bit, right, we just found a max flow. So what does that tell us? We have a max flow in this graph. What does that mean? Yeah? There's no augmenting path. If there's no augmenting path, what does that mean? Yeah?
There's a cut.
There's an empty cut, right? There's a cut of value 0. OK, what happens to this cut of value 0 when we scale in a bit? Each of the edges crossing that cut, right? It's a cut of value 0. All of the edges crossing that edge have residual capacity 0. Now we scale in a bit. So that means we double their capacity. So it's still 0. And then some of them we add 1. So every edge that was crossing the empty cut now has capacity of at most 1. OK? So after a phase, we have an empty cut, which is to say that all of the edges crossing it have 0 residual capacity. Now we scale. which means that we double and possibly increment. Each edge. And that means that each of those edges has capacity at most 1, which means that that cut has capacity at most m. Right? And that means that the max flow is less than or equal to m. Okay? So if the max flow value is at most m, how fast does the blocking flow algorithm run? Yeah. OMN, right? Its time is order NF plus NM. And that means that the overall runtime is order MN. So let me come back here because this may not have come out completely clearly. Right? This argument, okay, this works even if you have a capacitated graph. Right? So in the unit capacity case, all right, we measured the augments by saying that over all of the augmentations, each edge gets, right, when we do an augmentation, we destroy the edge. And so each edge only gets augmented once. And so the total work of augmentations is only order m. Right? Now, with a capacitated graph, that might not be true anymore. Right? When you have a capacitated graph, when you find a path and you augment through the path, right, you don't necessarily delete all of the edges on the path. Right? Because those edges might have different capacities, and the amount you augment by is determined by the minimum capacity. So other edges might remain. And so we can no longer say that the total work of the augmentation is order m. But we can still say, since every augmentation sends a unit of flow, that we can basically charge the n units of augmentation to the unit of flow that we sent. Sorry, that we can charge the work of augmentation along those n edges to the unit of flow that we sent. And that means that the total work, even in capacitated graphs, is order NF for doing augments. In contrast, the retreat argument doesn't need to change, right? When we retreat, it's because the edge is the dead-end edge, and it doesn't matter what its capacity is. We delete it. So the total work of retreating is order m. Okay. And as before, we can charge the work of the advances to the augments and the retreats. Okay. Yes?
Can you retreat in the capacitive graph? Because, I mean, at least in scaling, while in scaling, some edge may just suddenly appear. And that
Yes. So again, the argument about the time for a blocking flow is an argument that we apply to each phase of the scaling algorithm separately. So one phase of the scaling algorithm will take order mn time. And during the phase, we don't do any capacity changes, right? And so no capacity gets created, right? Except by the augmentations that we're doing, right? We create residual capacity. So, in summary, blocking flows give us an mn log u runtime for scaling max flows. And if you think back, this compares very nicely to the m squared log u running time that we got for an augmenting path algorithm. It's replacing one factor of m by a factor of n. And it's doing it for the same, intuitively at least, the reasoning is the same, that in augmenting paths, it takes you m time to find one unit of flow. But in blocking flows, you sort of amortize away the shortest path computation, and that means that it only takes you the n work of actually doing the augmentation each time you find an augmenting path. Make sense? Okay. So I've got just a few minutes left to sort of do a wrap-up around MaxFlow, because we're going to switch topics on Friday. So I'm not going to give details here, but let's first ask about strongly polynomial algorithms for, that are based on this blocking flow idea, right? So blocking flows seem appealing. They seem to be more powerful than the augmenting path approaches in the way they amortize work. But we have this nice scaling algorithm, but is there a way for us to use the blocking flow ideas in a strongly polynomial algorithm? The answer is yes. And essentially, the way that this solution was developed was that people said, I have this sort of general shape of a blocking flow algorithm in terms of advances and augments and retreats. Okay? So can I develop a data structure that will let me do a more efficient job of advances, blocks, and retreats? In particular, if we think about the capacitated case, so we've got this admissible graph with capacities. Now we start doing all of this advancing. And as we're advancing, we're tracing out a path in the admissible graph. And at some point, we'll get to the sink, and we'll say, aha, I found a path. Now, the way we've been implementing these algorithms so far, once we find a path, we augment along it. And in the capacitated case, that lets us delete one edge from the admissible graph, right? Because the remaining edges on the path might have larger capacities, and so they don't get deleted. Okay, so all that augmenting work, all it does is get rid of one edge. Okay? And so now there's kind of a waste, because if we go back to the source and start exploring again, we might explore the same edges as we used before, that we didn't delete. But if you think about it, if we deleted one edge, we have almost an entire path still remaining. If we could just kind of hook up the two pieces of the path that we used before, we would get another path. So the idea is to sort of keep these path fragments around. Okay? So basically, we start at S, we advance to T, and we find a path, and so we do an augmentation, and we delete the saturated edge that we augmented. Okay? Now, instead of starting again from S, we're actually going to start from here and try to explore in another direction. Okay? And maybe we will find another path to T, and when we saturate that, we'll delete something else. Okay? But we'll still have these sort of pieces of paths around. Okay? And we want to keep them. And sometimes we might end up doing a retreat. Okay? Other times, as we advance, right? So it may be that as I advance from after doing some other cuts and things, right? my advance may actually land me, it may attach me to another path that reaches all the way to t. Okay? So in fact, over time, as I do these advances and retreats and augments, I'm basically going to create a bunch of little trees in the graph that represent partial paths that can reach t. Okay? And what that means is that sort of when I advance, I'm going to attach the current vertex to the path from the next vertex. Okay, so I'm on some vertex x, and now I do an advance, and I say, I'm now going to join whatever partial path is hanging off of the vertex that I arrived at. And that partial path may actually be part of a tree that was formed by other paths joining in to this shape. Okay. If I want to retreat, this is actually called linking. If I want to retreat, I'm just going to remove that edge, which is going to cut my vertex from a tree that it is attached to. And finally, if I want to augment, what do I need to do? I need to decrease the capacity of every edge on the current path from S to T. Okay? And so the insight was that it was possible to develop a data structure that would allow you to implement these operations, linking a tree to another tree, cutting a tree from another tree, and somehow magically decreasing the capacity of a whole bunch of paths all at once, a whole bunch of edges all at once. Okay? Now, these seem, not crazy, right? That you can, we know how to add two trees and cut two trees by removing an edge, right? How can you decrease the capacity of a whole bunch of edges at once? Well, you don't represent the capacities on the edges. Instead, you represent the differences of capacities along the path, right? If you decrease the capacity of every edge, it doesn't change the differences of capacities at all. And so you only need to change one number to change the meaning of the entire path. Okay? So all you need to do is figure out a data structure that can do all of these things really fast. Okay? Who would you turn to if you wanted to figure out that kind of data structure? Tarjan, of course. So Slater and Tarjan developed these things called link cut trees that are able to do all three of these operations in order log n time per operation. And even better, they're built out of splay trees. So everything goes together. Okay? So essentially, you store your paths in splay trees that represent the paths, and you use splay operations to get the edge that you need to link or cut to the root of your tree, which you can then use to attach it to other trees. Okay? Really interesting. Once you're able to implement each of these operations in log n time, remember it was the augment that got very expensive in a capacitated graph, but now we've made the augment cheap again, and the result is that you can do max flow in order mn log n time using this blocking flow idea. Okay? And I'm finishing lecturing, like the formal lecturing of this class around Thanksgiving, and if there's enough interest in this kind of topic, I could give an optional lecture or two on some of the details of it. Okay? If you work harder, there was a long line of research that improved this to order mn log base m over n of n. Okay. This doesn't look like much of an improvement, but the point is that if the graph is dense, then this log term goes away. It's log base n of n, and so you're left with mn. And finally, many years after that, Orlin, who's a professor here at the Sloan School, managed to get it all the way down to mn using really sleazy techniques. Okay? Sort of like that optimal minimum spanning tree, like things you would never actually want to do, but they do give you the time bound, so it's worthwhile. For a very long time, mn stayed as the bound. For years, people were trying to push closer and closer to mn, and they thought that was sort of the ultimate. And Orlin finally achieved it. But at the same time, and there was a good reason to think of that, because our flow decomposition result, right, sort of says that you can break a flow into m paths, and each of those paths could be of length n. So it kind of feels like, augmenting on each of those paths seems like it should take about n time. So it seems like mn is a reasonable time bound. On the other hand, in the unit capacity case, we got these other bounds like m to the 3/2 and mn to the 2/3 and m squared of n. So Goldberg and Rao figured out how to extend those bounds to with scaling. So they showed that you could get m to the 3/2 log u and mn to the 2/3 log u and m root n log u for the bipartite case. Okay, so that unsettled things. And then the most horrible thing happened. The continuous optimization people came, the ones who like to talk about gradient descent and things like that. Okay. Ugh, like just don't get me started. Completely not combinatorial. There's all these derivatives and blech. Continuous optimization has led to a real goldmine of work here, where they've shown. Let's see, where are those crazy bounds? A guy named Madry, who's also upstairs, got us down to a bound of m to the 10�7 times u to the 1/7. So pseudo-polynomial, but better than m to the 3/2 by quite a lot. Okay, and in follow-on work, they managed to push it down. Some grad students here who did take this class, but I can't take credit for their work, achieved order m root n log u for max flow, not just for the bipartite case. And some more folks, including Kellner, who's over in the math department, have actually been getting approximation algorithms in linear time, modulo the approximation factor. Okay. And so this is actually still a quite unsettled area. It looks like there's hope that we're actually homing in on a near linear time algorithm for max flow. Okay, but we're not there yet. We've still got this error term to worry about. Okay. But if you are willing to put up with all of those awful gradients and things, there's still some pretty exciting work to be done in this space. Now, I hope that actually the combinatorialists will counterattack. Right? Now that we've shown that mn is not the real bound, maybe there's a beautiful combinatorial linear time algorithm for max flow. Okay, and so one little pointer in that direction is some work I did a long time ago with one of my graduate students, which finds a max flow in m plus nf time in undirected graphs. So, not getting anything like what's being achieved with the continuous algorithms, but at least it's replacing an m with an n in the small flow case. So I think there's still some opportunities to make progress in the combinatorial space as well. Okay. So that's the end of the story for MaxFlow, except it's not. So on Friday, we're going to generalize the problem. So far, we've been interested only in how we send the most possible flow. Now we're going to ask, what if it actually costs you something to send flow? So we're going to put prices on the edges, and we're going to ask you to find a minimum cost max flow. So we've just made the problem more challenging, and we're going to need to develop some new techniques in order to solve it. Yes?
I just want to let you know today is Friday.
What?
Today is Friday.
Oh, sorry. There have been so many Jewish holidays this month, I'm just completely lost in the calendar. So yes, on Monday, we will pick up with min cost flow. I'll see you then.